Welcome to our course on calculus. In this lecture, we are going to talk about the composition of functions and the continuity of composition of functions. What do we mean by composition of functions? Suppose we have two functions, right? Suppose f and g are two functions defined on, okay, let us take defined as f from a subset e of x to y, and g is a function that is defined from f of e of y to z. Okay, then the composition g composite f, this is the notation for composition. G composition f is defined as G composite f of x is g of f of x for all x in E. Okay, here what is happening? This composition is defined from x to z. Okay, now the natural question arises that f composite g exists or not. That exists only if the domain and codomain. Okay, in all cases, if we are considering x to x, then it is possible. Okay, or if we are defining x to y and y to x itself, then also it is possible. Right? So, diagrammatically speaking, what happens here is that we have three sets. Okay, f is some rule or a function that takes some element in x to some element in y. Okay, this we are writing as simply f of x, and there is some rule which takes every element y to some z. Here this we may write it as g of z. Right? The composition of these two functions is that it is going to take, it is a mapping from this x to z, which is going to take an element in x to element in z. How it is going to achieve this? This x can be mapped with this y, this we know. This y can be mapped with this z. So this x will be mapped with z. This is how the composition works, right? And this is a notation, right? This is a composition is a mapping from x to z, and some authors prefer to write this way and some prefer to write f composite g, and we will have to be very clear with what approach we are following. Right?
Let us see some examples of composition of functions. Let me consider my f of x to be 2x. Okay, and let me consider my g of x to be sin x. So here you are able to see how the function f of x and g of x behaves, and you may see this in the graph, right? Now I am going to make the composition g composite f. That is, I am going to input the value of f. Okay, I am going to input the value of f to g. So I am defining that function to be h of x. So what did I say? I am inputting f to g. So here you are able to see these things, right? I'll show you what exactly this is. This is the composition of those two functions. And in the comment section, you are able to see that g of f of x is what? It is sine of 2x, right? In the place of x in g of x, we will have to substitute f of x. That is how the composition works. And let us define the other way. The composition can be done in two ways. Only if the domain and codomain of both the functions are same. Here, for f as well as for g, the domain and codomain are the entire real numbers. Hence, the composition in two ways is possible. Now, I am defining this is, I am going to input my g value in f and see what happens. See, here you are able to see the function 2 sin x as well, right? So this is the This is the composition of f with g. Now, can you see the composition is not same? If we do G composite F and that and F composite G, in most of the cases they do not exist as well, because the codomain of F, that is the range of F, okay, the range of F has to be the domain for G so that the composition can be defined. Here both the functions have the range same, that is why we are able to define all these things, right?
Now let us see a theorem based on the composition of functions. The theorem tells us composition of continuous functions is also continuous. Okay, we have to prove this. How are we going to do it? Okay, since the statement is completely an abstract statement, we will have to name the spaces and the functions. Okay, let x, y, z be 3 metric spaces, or we may simply take metric spaces, because we do not know whether these are different metric spaces or the same set with different metric or same sets with same metric, we do not know. So let us consider these 3 are metric spaces, and let f is a function which is defined from e to y, where e is a subset of x, and g is a function that is defined from f of e, which is a subset of y to z. Okay, here what is f of e? F of e is the range of f. Okay, then we can define a composition G composite f from e to z by G composite f of x is g of f of x. So we have a function which is defined from e to y and another function from y to z, and we have defined the composition as well. And what is given in the statement? They have given that composition of continuous functions is also continuous, which means we will have to assume f and g are continuous, okay, in the respective domain, which means f is continuous in E and g is continuous in f of E. Okay, now for every epsilon bigger than 0, okay, since f and g are assumed to be continuous, I am just going to make use of the definition of a continuity. Now let me make use of the continuity of g. So for every epsilon greater than 0, there is a delta greater than 0 such that dz of what? F of x comma f of dz of g of y comma g of q less than epsilon whenever dy of y comma q less than delta. And this is for what? This is for all y comma q in f of e, right? Because the function is assumed to be continuous in the entire domain, in the sense this q may be any point and this y may be any point, okay? Or if you have to precisely say at all the points of f of e, then you may write for all y in e, okay, for every epsilon greater than 0 there is a delta such that these things are happening for all y in e, where this q is also a member of e, which means we are talking about the continuity at the point q, and this q may be any arbitrary point in, sorry, these are not from e, right? These are from f of e, sorry, in f of e. Okay, we will have to make use of the same thing again, right? So this is by continuity of g, we have written this. Okay, let us mark this as 1. Okay, now for every what are we going to do? We are going to make use of the continuity of f, right? So by continuity of f, for every, since we have given the notation epsilon and delta here, I am going to give another notation. Okay, epsilon 1 bigger than 0, there exists delta 1 bigger than 0 such that what is happening? Dy of f of x comma f of p less than epsilon 1 whenever dx of x comma p less than delta 1 for all x in E where this p is a member of E. Let us mark this as equation 2. Now just we have to combine these two things to get the continuity of this composition, and let us rename it as H just for the convenience. Okay, here what is happening? Whenever this is true, and whenever this is true, something has to be true. That is what we have to prove, right? So this p, okay, since we have fixed p here, this p will have a image in y, that is in f of x, sorry, f of e, it will have some image, right? Let us take that image as this cube. Okay, so for p in E we have f of p, and let us name that as, okay, let us name that as q in f of E, right? You may take this way or you may simply have f of p, that is no harm at all, right? And here this y and q are taken from where? These are taken from f of E, right? So all the elements of f of E can be written as f of x or f of p, some image of elements in E. That way also we may write. Okay, we will have to combine these two things. That is what we are going to do. Okay, so just now what we are going to do is that we are going to rename these notations. Okay, how are we going to rename it? Let me have this epsilon as it is. This delta I am taking as eta. Okay, here for this epsilon there is some eta, right? So here what am I saying? For every epsilon 1 I am saying, in particular I am choosing eta. So this, the same eta I am choosing here. Okay, and I am going to have this as delta. It is just a matter of convenience or renaming it. Okay, so what did I do here? I have had this as it is. For this epsilon I am able to identify some value here, and that value I am choosing, and for that value I am identifying this thing. Okay, whatever may be the value here, I am able to identify some smaller negligible quantity here. Remember, all these 4 quantities are negligible quantities. We may give any name to them, right? Now what is going to happen? We have this thing. Okay, so whatever may be the element in E, we can identify some associated element in f of E. Now what am I going to do is that if dx of x comma p less than delta, now what have I done? Okay, I should write this in red color so that you can identify the things. Okay, when this quantity is less than delta, then what will I have? then I will have dy of f of x comma f of p less than eta, right? And this is true for all x in E. Okay, now if dy of f of x comma f of p less than eta in the sense, what is going to happen? This will imply this, right? So I am going to get what? D is that of g of this value, right? So g of this value, g of f of x comma g of f of p less than epsilon, and this is true for all what? For all y in E. That is for all f of x in f of E. If I write f of x in f of E, this means what? All those elements in E will map to the elements here. So these two are equivalent. Now what did I prove? What we have done is that for every epsilon bigger than 0, there exists a delta positive such that d is that of this composition g of f of x. I may write it as what? Simply h of x. D is that of h of x comma h of p less than epsilon whenever dx of x comma p less than delta, right? And this completes the proof of this theorem. Thank you for watching.